Incomplete dominance is yet another type of pattern of inheritance to our ever-expanding list. And incomplete dominance is very similar to codominance, and I'll talk a little bit about that later, but if something is incomplete dominant, then the two alleles must express one intermediate trait, which means that it must blend together. Now, if something were to be homozygous dominant, it would just be, say, WW for the white chicken in the image, and homozygous recessive is just BB. They're both dominant, but we'll just put it for the sake of putting it. And then heterozygous would be WB, which is gray. Now, the difference between incomplete dominance and codominance is that in incomplete dominance, both of the alleles are mixed. They're expressed as one trait. While in codominance, we have two alleles expressed. So there are two traits being expressed at the same time. And if we look at the image, the Punnett square with the chicken drawings, we see that the outcome is all incomplete dominance and that they're all mixed.
Now, this is a practice problem on incomplete dominance, and it's about corn, and it goes like this. Incomplete dominance is a key element in improving crops such as corn. Corn with multiple incompletely dominant traits are generally healthier and provide greater yields than pure strands with fewer traits. The traits for yellow kernel colors are CY, and the traits for purple kernel colors are CP. The genotype CY-CP makes orange kernels. Cross a corn with yellow kernels, one that has purple kernels. List the different allele pairs and percentages. So as I write my Punnett square, I write the corn with yellow kernels crossing a corn with purple kernels. So CY crossed with CP. And I know that there's only one possible outcome from this since they're all going vertically and horizontally. So the only outcome is corn with orange kernels. So that would be CP. Now I'm going to write the different types of allele pairs and percentages. So I'm going to start off with yellow. So CY, which is yellow. And there are no yellow kernels, so that would be 0%. Next is purple, so CP. And there are 0 of those in the Punnett square, so 0%. And finally, orange, which is CP. And that's 100%. Cross a corn with purple kernels and one with orange kernels. List the different allele pairs and percentages. Okay, so I'm going to draw my Punnett square. I'm going to write the corn with purple kernels crossing the one with orange kernels. So that'd be CP crossed with CP. Now I write the allele pair types and the percentages. So CY, which is yellow, there's none of those, so that's 0%. CP, which is purple, there are 2 of those, so 2 out of 4 is 50%. And there's only 50% remaining, so we know that orange kernels, CP, have 50%. And that's a practice problem on incomplete dominance. Now the next pattern of inheritance, which we'll be looking at, is multiple alleles. And this means that there will be multiple alleles involved in this pattern of inheritance. And this is usually affiliated with blood type. So, for example, we have blood type A, blood type B, and blood type O. And the homozygous dominant for these blood types, for blood type A would be blood type A, and for blood type B, it would be IB. And the homozygous recessive is blood type O, so that would be lowercase I. And the heterozygous for blood type can only be IA, lowercase I or IB lowercase I. And this is because blood type A and B are not allowed to be together due to your immune system's restriction on that sort of blood type. Now, if we look at the image on the right, we see that there are two people who are heterozygous for blood type A who are having offspring. And this results in 3 people being blood type A and 1 person being blood type O. And because blood type goes with complete dominance, blood type A, lowercase I, is going to mask the lowercase I. So uppercase I, uppercase A, uppercase I, uppercase A is going to be phenotypically identical to uppercase I, uppercase A, lowercase I. This is a practice problem that has to do with blood type and focuses on multiple alleles in humans. As we see in the first chart, the allele I, uppercase A, codes for blood type A, which is dominant to blood type O and codominant to B. Blood type B is categorized as blood type B and dominant to O, is codominant to A, and lowercase I is categorized as blood type O, and that is the recessive allele for the blood types. Now if we fill in the phenotype for each genotype listed below, we find that blood type uppercase I, A, lowercase I categorized for blood type A. The second one is codominant, so that's AB, and lowercase I is blood type O. Now the first problem says a woman with blood type O and a man with blood type AB are expecting a child. What are the possible blood types of their baby? Show your work in a Punnett square. So as I draw my Punnett square, I list both of the parents' genotypes, which is uppercase I, uppercase A, uppercase I, uppercase B for one of the parents, and blood type O for the other parent, and I fill in the Punnett square and I find that the only possible results are blood type A and blood type B, which they're all heterozygous, in which the uppercase I, blood type A, or uppercase B masks the presence of the lowercase I, which is blood type O. As fill in, I categorize blood type A as uppercase I, uppercase A, lowercase I, because it's heterozygous, and that's 50% possibility for offspring to have that trait. And blood type B is going to be categorized as the same, except the A is replaced with the B, and there's only 50% remaining, so there's 50% chance that the offspring will have that genotype. And the next problem is, what are the possible blood types of a child whose parents are both heterozygous for blood type B? I'll show you work in a Punnett square. So I draw my Punnett square, and I find that it has to be uppercase I, uppercase B, with lowercase I, and the same for the other parent. Because both parents are heterozygous for blood type B. And I fill in the Punnett square, I see that there is a 75% chance of the child having blood type B, and a 25% chance of the child having blood type O, 50% chance of the child being heterozygous for blood type B, and 25% chance of the child being homozygous for blood type B. Now, Jill's blood type is blood type O. She has 2 older brothers with types A and B. What are the genotypes of her parents in respect to this trait? Well, I'm listing Jill and her brothers' genotypes, and I find that their parents have to be blood type uppercase I, uppercase A, blood type uppercase I, uppercase B, so they both have to be heterozygous for blood type A and blood type O. Those are the only possibilities because their children all have different varieties. See, one has a blood type O, one has blood type A, and one has blood type B. The test is done to determine the biological father of a child. The child's blood type is blood type A, and the mother's blood type is blood type B. Baby daddy number 1 has blood type of O, and baby daddy number 2 has blood type of AB. Who is the true baby daddy? Well, we see that the mother has blood type B and the child has blood type A.
So that crosses out baby daddy number 1 because he does not have any blood type, which is A. It is not possible for the baby to have blood type A if the father has blood type O. So you find that baby daddy 2 is the answer.